Hello and welcome to the KIM-1 Corner Part 9. This episode we'll be looking at this card here. Now this is the standard memory card for the KIM-1 with RAM in it and ROM. These are all 8K sections, so the whole addressing space of the KIM-1 I've been chopped up into 8K segments. So the bottom 8K is actually what's on the KIM-1 itself. And I've been using these EEPROMs up here for the programs I've been developing. Now, as you can tell from the previous episode, I'm running out of these and they're gradually wearing out. So I've had to do something different. Now, I did get some 8K EEPROMs to put in here, but they turned out to be no good at all, old ones. And 8K is a bit small these days, so if you want to buy new ICs, it's a bit tricky getting them that small. We ended up having to buy this one here. Oh, drop the camera. Well, this one here, which is 256K. So it's a lot larger than the KIM-1's memory space. But what I've done is I've sort of just chopped into segments. And seeing as this is just a testing board for developing the system, and I wanted to take the IC in and out all the time to program it, I'll put it on the ZIF socket. And this won't be the final board that you'll be running on, it'll be this one. What I'll do is I'll actually still use the EEPROMs, but I don't want to keep taking them in and out, and erasing them, etc. It's a lot easier with this one. So this is just for development, really. So put that to the side for the moment. Now if we look at this, we've got 256, oops, move that out of the way, 256K of EEPROM there. And this row of jumpers here, bring that a bit closer, where you see it says A15, 16, 17 and 18. They're the actual address lines going to this IC. A18 doesn't do anything on this one. There is a larger version of this that's 512 kilobytes, and that uses the top one. So that top one at the moment doesn't actually do anything. So if you'd got the 512K EEPROM, then you could use that as well. So these jumpers, by moving them either side in like a binary pattern, you can make this address different blocks further up in the memory in here. So at the moment we're just using the bottom 32K because they're all on zeros. Now this pair of jumpers here, this is to whether you want to be working in 8K blocks, 16 or 32, because we'll be using 16 at the moment. So by following these instructions, A14 is just put to 0 volts, and A13 is actually connected to the A13 that's coming in the bus up here, so it's addressable. So you can address 16K, but which 16K? That's where this row of jumpers come in. These are for the ROM. On the newer board it actually says ROM there and RAM there. I'm just going to be using the top two. So if you look on this board here, this one here, see the numbers there, says 8K7 and 8K6. So we've got 8K7 there and 8K6. So by putting these jumpers across there, the ROM will be selected when either of these control signals are true. And these other ones here just put down to pulled up to positive supply, and all these signals feed through to this IC here, which is just an AND gate really. So it ANDs them all together, and if either of these if any of them go low, then it gets selected. Well, these ones are all tied up to the positive rail, so they won't go low. But these two are actually on the chip select signals that are coming from the baseboard that they will plug into. And on the RAM side, same sort of thing. Where do you want your RAM? In this case, I've got it on 8K1, 8K2, 3 and 4. There's 32K of RAM there, starting in the bottom one. Haven't got 8K0 there. That's the RAM and ROM that's actually on the KIM-1 motherboard. So ignore that one, and this is in the next 5 spaces. Now there's a little bit of jiggery pokery that has to go on with these. The RAM is the easiest. You just select what ones you want it to be on, but you should have them all together. If you want 32K, it has to be a 32K block of RAM. You could move this up, so I could put this jumper onto 5 and take the one off the bottom, and then the RAM will be on 2, 3, 4 and 5. Or I can move it further up. That's equivalent to moving the RAM. At the moment, I've got it on that one, that one, that one, and that one. And if I move the jumpers up, I could have the RAM there, 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 and there if I wanted, just by moving these. You just have to make sure they're in groups of 4, or however many RAMs. I mean, there's 3 RAM chips there, so if I just used 8K1, 2, and 3, and put 4 back over there, those 3 pins would be exactly the same as these 3 ICs here, and this 32K RAM chip would act exactly the same as those 3. So that bit's quite simple. The ROM is a little bit more complicated. Now I've done a little presentation to explain how this works. But first of all, we'll have a quick look at the circuit diagram to this. So here we have the circuit diagram of the board. This is the edge connector coming in with the 8K signals that are generated by the expansion board, so we don't have to do the decoding all the time. And we've got here, there's the EEPROM IC. Up here you can select whether A13 or 14 actually do anything or not, so whether you're working in 8K blocks, 16K or 32K blocks. And these other pins here is where you select which 32K block you're using out of the memory space in here. So we'll only be using one at a time. Over on the left here, you see we've got 3 AND gates. Those 3 AND gates are in this IC here, which is a 74AC11. Just 3 input AND gates, simple as that. And so there's one there for the RAM as well, we'll come to that in a moment. I selected the surface mounted ones because I've got a whole bunch of them here from another project. They're easy enough to solder with a soldering iron if you're not into surface mounted. Or I could redesign the board to put bigger ones on, but they work just fine. So that's those 3 there. And you've got your 8K signals here. So these are your 7 different chip selects coming from the expansion board. Come through to the 3 jumpers here. 3 jumpers going across there, there. Well, the top one here is 8 of them for 8K0, but that's not actually used, that one. I could have missed it off the board. So you've got 3. You can either have it on the positive supply, or you can have it on the 8K signal, and the centre one, which is in blue, is what actually feeds up to the IC. Well, sorry, it doesn't feed to the IC, it feeds to the AND gates, then the AND gate feeds to the IC. And that's those 3 there. So if all the signals are 1, then they're all at 1, and the output here is at 1, and this EEPROM is not selected. If one of the chip selects that you've chosen gets operated, it goes low, then you lose one of the signals to these AND gates, and this output will switch low and chip select the EEPROM. Therefore you can select various ranges of them. Further down here, there's the 32K RAM. You just got your bottom 15 addresses lines coming in. And over here to the left, we've got the same arrangement with 3 AND gates. So you've got your 8K1 to 8K7 chip select signals coming in, and you select which one you want to use. It's either positive supply or the signal comes through here, and that's fed onto the AND gates. And then when one of these goes low that you've selected by your setting of the jumpers, then this output will go low, and you'll get your chip select onto your RAM. The actual selection of what ones are going to be in what area is not quite so straightforward. We'll have a look at that now. So to start with, this is the EEPROM. The one I've got is 256 kilobytes in size. They do, in this particular range, 128K, a 256K and a 512K. I picked this one because it was £3, and I'm going to use it on other projects as well, so it was worthwhile getting a bigger one, and we just used some of it on this project. So in my instance, that you can think of that as being chopped into 16 32K blocks, which will be selected by these jumpers here. So we're on 0, 0, 0, 0, so we're on block 0, which would be this block here. So just by changing those jumpers, just select whichever one. So this will actually be the bottom 32K of that EEPROM. You remember that for programming. Using one of the other blocks, then you're going to have to offset the code when you program the IC. What you could do is you could have different versions in each block, and then you could, just by changing those jumpers, boot up a different version. So A15 to 18 selects those, and then we've got this arrangement. So each one of these 32K blocks you can think of as being chopped into 4 different sections. So each one of those 8 sections is like one of these slots here. So in this instance, we're using 16K, we're using 2 of them, 8K7 and 8K6. If you wanted just 8K, just one equivalent to 1 EEPROM, we could just use the bottom bit here, an 8K block. Or we could use 2, which would be 16K, or you can do a full 32K. Now, if you're just using an 8K, just one 8K, so that's one IC, well, where do you want it to go? Well, you can go into 1, 2, 3, 4, any of the 7 slots you could put it in. So any one of these slots can be basically selected by changing these jumpers here. Yeah, that's where you select where it is. So we're going to use 6 and 7, which is the same as 6 and 7 here, which would be these 2 at the top here. Now you want to keep them next to each other, otherwise you're trying to split your ROM across from there, say, to there. You could do it, but there's a few caveats to doing that. If we look at the next page, so if you want to do 16K, as we're using, you'll be using, out of your 32K page, you'll be using the bottom 2 lots of 8K, in this instance anyhow. So 16K, and that could be either those ones at the bottom there, or these ones here, or these 2, or these 2, and we'll be using those top 2 there. What you can do is, if you want to do, say, 2 of them, that are not even blocks, you want to spread your 16K across this one and this one, what you'd have to do is you'd have to select a 32K block from these jumpers. So we'd have 8K 1 and 2 selected there, but they're not on an even address because we've got 8K0 there. So we're not putting it in evenly. So we're sort of across blocks. And what that happens is, in the actual EEPROM, which got a 32K block addressing in here, that's trying to come in at this level here. So we're just using these 2 blocks to fill in those spaces. And what you do is, this one you have set so it's not used. So for that bottom one, well, there's no jumper in there anyhow. And this top one here, that would be in 8K3. But if we leave 8K3 set to off, as into VDD, then when 8K3 signal comes along, although that's sort of within that stressing range, that won't actually be selected because it won't get selected through that chip there. And you could have something else in there. Like you could have the RAM going to 8K3 as it is here. So all you've got to remember to do then is, when you're programming the EEPROM, you offset everything by 8K because you're sitting in the middle here. This is your whole 32K block that you've got to use. You've got to shift all your code up. Now, if we go for a 32K block, you'd be looking at doing it in every 4 blocks of 8K. So you'd either be on the bottom one or on the top one. Now, you might want to do it overlapping, which is a lot more likely. So what you'd have to do is, if you wanted to do, say, 1, 2, 3 and 4, so that's the bottom blocks, you wanted to put ROM in there, there, there and there, then you'd have to do a 32K block and tell it to turn on when these chip selects are selected. But what you'll find is this bottom part here of your 32K block will actually appear up here because the extra address line isn't actually decoded for it. So you'd have to offset all your code by 8K up here, and then the bit that would normally sit up here, you'd have to burn down there, and it would appear at that location, which is a little bit messy really, but this is only for development, it's not for full-time running. Again, if you wanted to move the addressing spaces up, so you've got the same configuration there, but you could make it so the chip selects it here. So the top half comes in here, and the bottom half will be fed up there. So you could do 8K 2, 3, 4, and 5 with your ROM, which is equivalent to having your ROM in, oh, which ones would that be in? That'd be in this one, this one, this one, and this one, leaving the RAM there and whatever. But what you'll find is you'd have to offset your programming by 16K, so that the bit that comes in here, it will have to be in the top half of your 32K you're going in, and the top half that you want there will have to be put into the bottom half of the 32K of program that you're programming into the EEPROM. That's not so likely to happen on the development board. Because what I'll do, as I said, I'll just actually do proper EEPROMs in the right place on the final bit. And you could even do this arrangement where you're up the top here. You're not using the top one, but the next one's down, which is the same as using this one, this one, this one, and this one as EEPROMs. In this case, if your bottom ones will be sitting up here, and that one's there, this is like a 24K offset. This may seem a bit odd, but if you was going to be using just the top 3 here, you just wanted to use the top 3 ROM slots like here, here, and here, which we did earlier in the series. We had 3 of them in here. Then you would have to have it set to a 32K block and addressing here, here, and here. But this bottom one you then have deselected. So this 32K will actually be sitting right on the top here. And you just don't use the bottom one. And then you have 24K of ROM there, but you don't have to offset your code so that it doesn't get written into this bottom one. It starts at this point here. Just have to remember your addresses. Now the RAM is a lot simpler. You look at the RAM. Again, you've got 32K of RAM. You might want to use 8K of it, and you can select whichever one you want it to go in. You can go into any of them. So on your RAM, you've got your, as shown before, there's all your jumpers, and you just decide which one the RAM's going to answer to. The only rule here is if you're using all 32K, they should all be together. If you're using 16K, then they should both be next to each other. So I'm just thinking of the 8K at the moment. So we just decide which slot has got the 8K in and select whichever one we want. If you're using 16K of RAM, then that can be in multiple places. You could start at the bottom and work your way up, all the way up to the top. So you could have RAM in these 2 spots, if you're doing 16K, or those 2, or that one and that one, or those 2, or those 2, or those 2, whichever you wanted. The only thing is to keep them both together. Because if you don't, and you split them up, you may find that this location will answer at the same time as that location. Well, depending on how many you've got in there, maybe over here, it's what actually happens is the RAM does get shuffled around where it's written to, but when it goes in, it goes into the wrong place. But when it comes out, it goes back into the right place. Where you address it from doesn't matter, just as long as it goes in and comes out in the same location. So the RAM works out somewhat easier. So any 2 there. If you wanted to do 32K, then it's just pick 4 of them, but make sure all 4 are together. Because what will happen is in this instance here, we write into these locations here normally. If you've got this configuration, then you'll find that this bit of memory is actually addressed there. This bit is addressed there. This bit is addressed there. And then when you're addressing that, you're actually using this bit of the 32K block of RAM. It doesn't matter because when you're feeding in, it goes into the bottom, and when you feed it out, it comes out. So it's all the same. It gets shuffled around. The only time you have to remember this is if you had a gap in the middle. It's all to do with which addressing lines have been addressed for where. Again, I'll say it's only a development board, so it's not too important. It's a bit fiddly. So the RAM is a lot easier. Just keep them all together. What you can do if you want to, if you're really desperate, is you could plug both of these boards in at the same time and as you see, this 32k RAM is this 32k RAM here is selected for 1, 2, 3 and 4, and the ROM is selected for 6 and 7. There's nothing in 5. So what you could do on this board is put a RAM chip in that slot there and take the others out, and thus you could fill in the odd blank. You could have what's that, 5 times 8, that's 40k of RAM. I'll fill in that one in. And if you didn't want all the basic etc. in, you could just use your, as you boot up ROM, you can put RAM in there as well. So you can have 2 RAMs in this board and then use this one to fill up the others. Therefore you get 6 slots of 8, that's 48k of RAM in there. You'd be better off having 2 of these boards. It's a lot easier to understand what's going on. Well, no, you don't need 1 of these boards. Just have to have lots of these ICs. I've only got 4 of them, and I've got 2 of these boards to fiddle around with. So I've got a whole bunch of these 32Ks. So that's why I stuck a 32K in there. It's still recovered off another board, but there you go. So to program this is a little bit different from doing an EEPROM. We go to programming it. Here we go. So we'll compile the latest version, and then we can oh, wrong way, that one, and link it all. And now we should have sitting in the compiler's directory a new version of the monitor ROM ready to go. So we need to program that in. So we run up the programming software. We take that out of there. One thing to remember is these are pin 1 down and the programmer is pin 1 up. So make sure we turn the IC around, drop it in, lock it in, and on the programming software we make sure we've got the right IC selected, because these are EEPROMs, not EEPROMs, so there's no programming voltage, etc. Now let's load up the latest version. Here we go, just there, we just compiled it, we just made it this very minute. Open that, and then we can just, there we go, it's all sitting in there ready to go. That's just 16k's worth of stuff. Where are we? And then there's the rest of the memory, nothing in there. We've got 16k to go. Let's program that in. There we go, it only programs the section it needs to program. So if we scroll down here, there's sort of, basically let's read it back just to make sure. Alright, I've just read the whole lot. And where are we? That's what we got programmed in. This is all MS Basic. And we keep scrolling down. It's the end of MS Basic. Then we've got some blank bits. And then we've got the actual new monitor ROM sitting in there. We'll be going into more detail in the next episode. Small bits of it, and that's the end of the actual monitor ROM that's got code in. We keep going down. We find, oops, there we go, there's the last bit, and here's our reset vectors. So this here, 4000 onwards, would be the next page in there, the next 32k page, so you could have another chunk in there if you wanted to. But we're just using that top bit. If we pop that back into the actual board, so take it out of there, and remember to turn it around again. Plugged in there, and then we'll unstick that in the KIM and check that it boots up okay. So here we are back at the KIM. Let's plug this in. Okay, it doesn't matter which slot, but as soon as this got this ZIF socket here, it sticks out a bit, so it's best to put it in the first slot. Right, if we power that up and press the reset button, let's run up PuTTY and see if we've got anything come on. So it's PuTTY. We're on COM3 normally, I'll guess at that. Serial, none, burn, and there we go. Let's bring that to the middle. If we slightly different on this newer software, I'll press M, we get a menu now. So this is what I've been working on. You see you've got this save data to solid state drive, load data to solid state drive, list file, delete file, and there's read page and write page. These are all solid state drive. So that's this, which hopefully will be in the next episode. I've still got software to do on it. I've still got stuff to write and I haven't debugged any of it. So anyhow, so this is the solid state drive, that little tiny chip there, well, that's the memory in it, and this is all the control for it. We'll go into that detail in the next episode. That's these options here, these first ones. They won't work at the moment because they're not plugged in. And I've moved these other bits over here. So you've always had L and Q for load and save of data to the terminal. It's a paper tape output, so they still work. You just type in the start address you want to send out, how much of it, or end address rather. Oh, that's gone wrong. If I press escape, it will dump out of it. So I'll do it again. So save 2000 to 4100, and there we go. Whatever sitting in that memory location is dumped out, and we can load in exactly the same way as before. Number 9, memory block listing. We covered this one in an earlier episode as well, so you can look to see what's there. Keep going through them. So we escape back here, and again Microsoft Basic. You now press A. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9. I could have had a 0 there, but in the future, if there's multiple levels of menus, 0 would be to go back to the previous. So it's A, B, and C. It will be like in hexadecimal. So A, there we go. Straight into your basic. You notice we've got 32K of RAM sitting here this time. Across here. And here we go. 10 int note error. And 20.2 10 run. Same before. And break out. Go on, break out. It all is there. Now I've got to reset to get back to the menu from basic. Now if we look at the memory block, we now go to 2000. And we do look at that. See where it says it's up here? That's the actual basic program. Starting, I'm not quite sure what the first characters are, I've got to work them out, but there's the basic program. And within MS Basic, there's a couple of variables that tell you where the beginning and end of the basic program is. So I was going to create a couple of commands within MS Basic to save and load the basic program. And that will be going to the solid state drive. And you just use those two variables in there to know where the beginning and end is. And when you load it back in, you load it back there and you'll be ready to run. So it's a quick way of loading and saving basic programs. Escape out of that. There we go with a newer board that helped development a bit faster, I think. Here we've got the, bit close up, the standalone board with its own processor card in it and comms. And this is the memory board for that. So we can take the memory board out of here and it can take the board out of the KIM and we can plug it in this one in your slot. So now we've got process CPU card that we built previously, comms card, and the new memory card in there. So this is sort of like a standalone little KIM. So let's power this one up and check it works on here. So supply off, comms off. Let's move the KIM out of the way. Oh, and now let's try the standalone one. Comms port in, Get the power supply on the right way round. There we go, all plugged in. And let's turn that on. And press the reset. And let's see what we get come up on the screen. Let's see if we can run up putty again. Should be COM3 still. And turn that off. And hey, there we go. We're working on the standalone as well. So we should do, because the standalone CPU is designed to be just like the KIM. There we go with a newer board that helped development a bit faster, I think. And hopefully we'll be working on the solid state drive. You may have noticed solid state drive's got a serial port here as well. And this is allowed to talk to a PC. So while it's plugged in, it'll be the KIM, and you could come through here and actually access the solid state drive from a PC and change the data on it. So you could use it for backing up or different images, or just put in programs on there that you've got off the internet, etc. Or compiled. You could drop straight into the memory. We'll cover that in the next episode though. So hope you enjoyed this, and don't forget to like and subscribe, and hopefully I'll see you in the next episode.